In this section, we will look at normal probability distributions. If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, and that can be described by the following equation, we say it has a normal distribution. The empirical rule applies to the normal probability distribution as shown here. Here are a couple properties for probability distributions. The graph of a continuous probability distribution is called a density curve. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. An example of a uniform distribution. Probability from 0 to 2 will be 0.5 times 2, which is 1. Example B, we want the probability of being from 1.5 to 2. Let's shade the region that represents. From 1.5 to 2, the length is 0.5, and the height is 0.5 as well. So we multiply to find the area, which is also the probability. Example C, we want the probability of having exactly x equal 1. There is no length, so 0 times a half is just 0. Here's another example of a uniform distribution with Old Faithful. This is a pretty straightforward example, but let's use the uniform distribution for practice. From the picture, we want to find the area of the blue portion of the graph. This will be the probability we want. The area of the blue portion is calculated by multiplying 1 over 91 times a plus 20 minus a, which simplifies to 20 over 91. Then rounds about to 0.22. If you wait 91 minutes, you're guaranteed to see Old Faithful erupt. Now, let's look at the standard normal distribution. To be standard normal, we need these following properties. Since we don't have calculus to find area under the curve, we use statistical tools to help us out. Here's how we find probabilities when given z-scores. We can use this wonderful table to help us out. Or we can use the calculator too. We will look at the calculator a little later. First, we do some by hand and the table. Some notation. Z-score is the distance along the horizontal scale of the standard normal distribution. Area is the region under the curve. And here is some notation for reading the probabilities. Now let's try some examples. Reading the problem, we can see that this is a standard normal distribution. Example A, we want to know the probability of drawing a reading of -1.5 degrees Celsius or less. Writing it in probability notation, now let's draw a diagram. Now we look at the table for z-scores and the corresponding area to the left of the z-score. On the table, we want -1.50. So look at the far left column for -1.5, and then the upper row has the last digit, which we want 0. And the highlighted area is the area we want, which is 0.0668. Example B, we want the probability of a reading less than 1.23 degrees Celsius. Again, writing it in probability notation and drawing a diagram. Now we look at the table with the corresponding z-score of 1.23 and the area to the left. And here is the highlighted area that represents our probability. Next example. Here we want the probability that the reading is greater than 2.22 degrees Celsius. Writing the proper notation and drawing a picture, the table only gives area to the left of the z-score, but we want the area to the right. So we need to rewrite the probability in a way that will give us the area to the right. Using the table to find the area to the left of the z-score, 2.22, and we end up with our result of 0.0132. Example D, we want to find the probability the reading is greater than negative 1.96 degrees Celsius. Drawing a diagram, we again see that we need to rewrite the probability as 1 minus p of z less than negative 1.96. Since the table only gives area to the left of a z-score. Now finding the area that corresponds to the left of negative 1.96. And we get 0.9750 as our probability. Next example, we want the probability of being between 0.5 and 1. Here we need to rewrite the probability as the larger area to the left of the z-score 1 minus the smaller area to the left of the z-score 0.5 to get our desired result. Now we use the table to find the z-scores and their corresponding areas to the left of 1 and 0.5. Highlighting those areas. And then we just evaluate. And we get 0.1499. And the last example, we want the probability between negative 2.87 and 1.34 degrees Celsius. Drawing the diagram. Again, in order to use the table, we need to rewrite the probability as the larger area minus the smaller area. Which is P of z less than 1.34 minus P of z less than negative 2.87. Looking at the table to find those areas that correspond to the z-scores, now we just take the difference and we have our answer. Now let's look at how to do this on our calculator. To do this, we click on second, then vars, scroll down to normal CDF, then enter from left z-score to the right z-score. In example A, we use -10 as our left z-score since it is really far from the mean of 0, and the right z-score is -1.5. And we get the same answer. Example B, we do a similar process using -10 as the left z-score and 1.23 as the right z-score. Same answer again. Example C, same process except here our left z-score is 2.22 and our right z-score we choose 10 since it is far from the mean 0. And same answer. Example D, same process where -1.96 is our left z-score and choosing 10 as the right z-score. Example E, same process where left z-score is 0.50 and the right z-score is 1.00. And again, same answer. Last example again, same process where left z-score is -2.87 and 1.34 as the right z-score.